Welcome. It's my honor and privilege to introduce one of my colleagues in the Department of Computer Science here at SDSU, Professor Hajar Homayouni. She's an assistant professor. Her research focuses on estimating and addressing existing issues with imbalanced and faulty data used for critical decision making. She has a bunch of cool awards, CASI, LREU, and STARS Computing Corps fellowships for diverse student support for research, as well as a Google Cloud grant to support COVID-19 research, which maybe she'll talk about today. She's been played all kinds of roles in different academic conferences, journals, all kinds of international venues. And she teaches here data science, introductory and advanced, so graduate and undergraduate. Cool. So thanks.
Thank you so much, Danny, for the introduction. Hello, everyone. As Danny says, I'm Hajar, and I'm glad to be here to present my research. It's an honor for me. As Danny says, one of the focuses of my research is to address issues with data. And one of the important issues with data-driven models and any project that use data is there is no sufficient data. The incompleteness of data sets, as well as the imbalances in the data set. These are some of the major issues. So with that respect, I'm going to talk about one of my papers that has been recently presented in ACM Health Informatic Knowledge Management Conference on synthetic high-resolution COVID-19 data generation. So I'm going to talk about it. Let's first define the problem. So after the pandemic, you may have seen many different deep learning and machine learning models trying to use COVID-19 data for different tasks, such as prediction, diagnosis, etc. So having a good generalizable model requires sufficient data to be trained. However, in terms of COVID, there was not enough data, especially at the beginning. And even now, we don't still have sufficient data in many cases. Even if data is available, because this is related to patient data, this is confidential because of data privacy and confidentiality issue. Not many researchers access the data. So there is a requirement for some sort of fake or synthetic data that actually mimic the actual data. Another issue with current data sets, although they might be available, they are imbalanced. So if we have different classes of data, the number of records for each class is not equal. So typically there's still the distribution of data towards a specific class, and there are biases in those data. So my focus of research is generate synthetic data. Because we know accessing adequate balanced data is critical for any modeling technique.
That's a question.
Sure.
How would you know that what you fabricate is reliable?
So there are some measures, some metrics that we can actually evaluate the quality and diversity of the data, and I'm going to talk about it. Thank you for the good question. Yeah, sure. So there are a bunch of approaches for synthetic data generation in COVID-19. What are their limitations? My focus of this research has been generating COVID-19 long X-ray images, because these are one of the most effective tools for diagnosis and different types of research in COVID-19. So the existing synthetic COVID-19 X-ray generations are not generating high-resolution images that can be useful by researchers and medical experts. And also, the generated images do not identify the disease level, or what is the severity of the disease in that patient, or is it either from a normal or a COVID-19 negative patient or COVID positive patient. So that information is not available in those tools. So the research objective have been using the limited available X-ray images of COVID-19, which are publicly available, to generate balanced and diverse COVID-19 images. So why do I say diverse? Because we do not want to replicate what we already have. We want to generate new data, new patterns in the data that does not exist, or at least is different from what we already have. And so with that purpose, we developed a framework called HRCX for high resolution COVID-19 X-ray generation. And this framework is based on two different deep learning models. One is generative adversarial network, and the other one is the predictive model to generate the data. Here is an overview of the framework. It takes limited available COVID-19 X-rays as input and generate fake data as output, as well as severity score for each of those images. There are four major components, as you see in the boxes. Data preparation, pre-processes the data, transform it into a form suitable for analysis. Image generation is the major component where we generate fake images using a generative adversarial model. Super resolution improves the resolution of generated images, so it can be more useful or helpful for the experts of the domain as well as the researchers in the area. And finally, COVID-19 severity estimation component estimates the severity score for each of the generated images. I'm going to talk about each component in the next coming slide. So in general, the data we used were from three different resources. One was X-ray data set on Kaggle, which is a public repository for different data science projects. And it includes both normal and COVID-19 positive large X-ray images. There were two other sources that we used for severity score calculation. And these were data sets which were labeled by severity score through domain experts, radiologists. And the pre-processing is was actually converting image to TensorFlow records, which are sequences of binary strings. So these to be used for by the model we were using. The next component is image generation. We use a generative adversarial network that are popular in generating fake images of faces, and we wanted to apply the same model to generate fake COVID-19 data. So in general, what is a generative adversarial network? It is a deep neural network consisting of two competing components. One is a generator and one is a discriminator. The generator objective is to generate fake data from a latent space, and the discriminator objective is to distinguish between real and fake data. And these two components are trained in a competing manner in order to improve or actually fool each other. So the generator objective is to fool discriminator by generating realistic images. After the training process, we expect that the output will be images that are very close to real. There is a problem with the original GAN network, and this is they don't have any control over the generated images because they start from totally random or latent space without so the generator itself does not have any control over the images. The style GAN is an extension of GAN network that adds some controls over the style of the generated image. I will talk about it in the later slide. And also, it can generate more diverse images by using two different sources of randomness in its structure. So in the image of this slide, you can see an example of style gap being used for generating fake images. So there were two different sources of original data or actual data used to train the model. From source A, the network has captured gender, age, hair length, glasses, and pose. And from source B, the network has captured everything else. And the four images are the new fake images generated by the model. So we use the same idea for the COVID-19 data generation. So here is a little bit more detail about the style GAN network. So if you compare the traditional GAN with the style GAN, the traditional GAN has input from or randomness received from one source of latent space, and it is passed through multiple convolutional, non-convolutional layers until generating data of expected dimensionality. However, in a style GAN, you have two different sources of randomness. The first resource is this latent space that is passed through a mapping network. And what this mapping network does is transforming the input into a style vector. So this part by itself is a neural network that maps the random space into a style vector. And the style vector is actually encoding information style of each feature map. It can be color, texture, hair color, so different details of features of image, and is encoded into this vector that are integrated into the generator model through different layers and used by the model to actually generate the images based on that feature. The second source of noise is added to the model through these noise vectors, and at each point of generator model, this noise is being added. It will result in more diverse image generation as well as kind of overcoming or overfitting of the network on the training data. So after we use style GAN, and you will see some examples of the image generated, we improve this resolution using a super resolution algorithm. The super resolution algorithm by itself is a deep network, has a deep network structure. It is called progressive reconstruction network. It actually takes an image and it improves its resolution. And it has been a very popular tool to improve the resolution of images from different domains. This network has two components. It has a feature extraction branch and an image reconstruction branch, and it looks like a pyramid. So it has a pyramid architecture that improves the resolution in different steps. So the approach is having the input image. It actually extracts the features of that image into some vector, and then upsamples the feature through multiple post-convolutional layers to output the residual image. And it actually adds this residual image to the interpolated input image to generate the high resolution. So this step is repeated multiple times until generating the output a high resolution image. Here is an example of the generated images and its resolution. So in the left side, this is the original image of the COVID-19 positive patient, and in the right side you can see the generated image are from a good resolution. And we also asked radiologists to confirm the quality of the data. You will see some standard metrics that we use to evaluate the So the last step was severity estimation. So for this purpose, we use the DenseNet model. So what this DenseNet model do is actually a model used for different regression problems. And here the regression problem was estimating a score. So it has two steps. One is feature extraction, which extracts some features of the image. And the next step is using a simple linear regression model to estimate the score for each of those images. For evaluating what we had as generated fake images, we defined different objectives. The first objective was we want to see and evaluate the quality and diversity of the generated images. Like I said, we wanted to have a diverse pattern of images in the output. So we needed a metric that can calculate this information. The next thing was to evaluate the resolution of the images, and lastly, the effectiveness of our approach that calculates and estimates the severity score. To evaluate quality and diversity of the image, there is a standard metric, FID, pressure inception distance, that is used in the area of synthetic data generation to make sure that the generated data is of high quality. This metric, although it is very popular and used by many researchers, but along with this metric, we also ask two radiologists to confirm the quality of the generated data. So you can see the equation for this metric calculation. So what it does is capture the similarity of the generated image with the real or actual image, as well as calculate the intra-class diversity. So at the same time, it considers quality and diversity calculation. In general, we are looking for a lower value of the FID score to say an image is a good image. And if you look at our results, you can see that the StyleGAN model that we use and compared to state-of-the-art models used for COVID-19 generation data improved the FID score considerably. The next evaluation objective was to evaluate image resolution. So there is another standard metric that is used to evaluate the image processing methods to make sure that the new image is of high quality when compared to the original image. And this is called peak signal to noise ratio. It is defined as ratio of maximum pixel value, which is based on the bit depth of image and to the mean square error between original and processed image. So in this calculation, we are looking for a higher PSNR value to say that the method is a good method. So like I said, the resolution, super resolution method that we use was lab SRN, and this has the second highest value for this metric. The first higher value is for an algorithm called EDSR. So this one, although has a little bit of higher in terms of PSNR, but it takes way longer to run this algorithm against the image. So for increasing the resolution of one image, it took 20 seconds for lab SRN versus an EDSR, which takes 700 seconds. So we prefer to use the second best approach because of the purpose. And lastly, we evaluate the effectiveness of the severity score prediction. There were two metrics that are used by the experts to calculate the severity score of the long X-ray image. One is the geographic extent and the other one is the degree of opacity. So we measured those two metrics for both normal and COVID-19 images that are fake as well as real. And we made sure that these are in the same range for synthetic and versus real images. So we measured that one and demonstrated that they are in the same range and that can be distinguished between COVID-19 and normal images. In conclusion, we proposed a framework for COVID-19 X-ray generation. So in general, the images that were generated in terms of quality and diversity outperform the state-of-the-art methods. For the same purpose, we could produce high-resolution images and added Severity score. In general, we generated 3,300 high-quality and diverse images, and we made it available for researchers to use. We increased the resolution of those images to 1024 by 1024 with the help of super resolution. And also we calculated the severity score for a subset of images, but we made that available for other images to be calculated by them. So there are two directions that we are working on for the next steps. One is we are interested in generating rare occurrences, such as patients who are, for example, diagnosed with both lung cancer and COVID-19. So these are very rare cases that the images are not available or not many cases to be used by the researchers. So we are training our model with subset of data from both categories to be able to use a style GAN to capture features of those two cases and generate images that combine both features. And the other thing is we are interested in generating multimodal data. So for example, we are trying to generate both image and its caption. So along with some COVID-19 image, it would be nice to have the caption like a description of the image to help the researchers to understand the image better. So we are using available data to train our model and adding the multimodal features to actually be able to generate that type of data. Thank you so much.
For the style, I know what you're talking about for that input space. So what was the information that you included for that for the effort specifically? Because you were talking about how, like, hairstyle or color the input for the generation style of spirit directors, what that was.
So actually, these are something that is learned by the mapping network itself. It is not something that I identify, but my expectation for COVID-19 images is to capture like the opacity or geometry of the the areas of the lung that is infected by the COVID-19. So I expect those features to be extracted by the network, but actually those are learned by the network. Yes.
When you're going to generate an image that was going to be in this COVID-19 and lung cancer class, how do you tell it to generate one of those?
So you remember I showed an image of people with different, that the style GAN model can capture different features from different groups of people. So what we are trying to do is training the model from with the patients with lung cancer and patients with COVID-19. They don't have both at the same time, but we have images of separate categories. So by training the model on those categories, we expect that the network can combine the features of those groups and generate images that have both disease. And for evaluation would be challenging because it definitely requires some expert feedback to make sure these are images actually makes sense. Yeah.
How much compression is involved in going from the raw down?
So by compression, you mean
Yeah, just how much information is, is started, I guess. I mean, just how much data, I guess. I mean, you have 512 by 512 pixels. That's a pretty big space. How big is the feature space?
so I understand your question. So it depends how we design the network, but I don't remember what was the size of feature space in our network. But I believe that when we are using deep learning layer by layer, it is capturing important features, and in the most hidden layer, even if the number of features is small, it is capturing the correlation between features of previous layers. So it is capturing the important information of that big image. And so throughout training, these relevant features will be captured and their correlation.
Yeah, I mean, I'm just curious how much of what's in the raw images is not relevant information, I guess.
Yeah.
What I'm getting at, I mean, how many features do you need to represent variation data?
I understand. Yeah.
I mean, how you must know how big your feature vector is, right?
Yeah, the input feature vector is equal to the image size.
Oh,
So,
it is.
yeah, but throughout the network it will decrease definitely.
So you don't actually count features, do you?
So you mean the feature extraction is done through the network
It's
itself?
all inside the deep net.
Yeah.
Can't
The
touch
input is the input is the image.
Right, so that's actually why I was wondering how you get to combine features you get to know the features to combine it for the cancer and COVID.
That is exactly what the feature extraction does. So it's the feature extraction layers extract features of each, and then in next layer it combines them. So in upper layers, it extracts individual features from each category, and in the next layers, it will combine.
Question from the chat. What sort of hardware was the network trained on, and how long was the training?
So good question. So the training time, I think for that number of for the 3,300 images, it took about multiple hours to be trained. So it was done overnight on hardware with one GPU. So this was done by one of my students. So yeah, this computation is long. So this is the problem with generative networks. They are computationally complex. And I think the next generation of which are transformers are addressing the problem. So maybe one of our next trials will be try some transformer-based model to do some parallel processing in terms of the training and improve its make it competent.
It will benefit from a GPU cluster.
You mentioned evaluation, so you had some statistical methods to do evaluation of your different components, and you mentioned some cases you checked with radiologists as well. Just curious, how did the comparison between the feedback from people and the statistical methods, were they in line, or were they any notable cases where they diverged? Or?
They were pretty much in line. So what they read. So the radiologist didn't, I have the detail in the paper, but they didn't check all of the generated image. We randomly selected a sample and asked them to evaluate. So first of all, they said whether it is a COVID-19 patient or not. So we check both cases, non-COVID-19, COVID-19, and yeah. The severity score calculation looks reasonable for them for that images. And in general, they also said whether or not this makes sense, because when we first started this project, some of the images, although they looked like some actual chest X-ray, but when checking with radiologists, they said no, this is not the quality we are expecting. So by using this method, we could come to that quality that's acceptable by a radiologist too. That is realistic enough.
Did you use any of that feedback in training the networks, for example, or any of the processes revisit?
So we didn't incorporate that feedback in the processing, but actually we did the checking for the 2 times. One step was using an original GAN network, and they said no. So that was why we tried to use the next generation of networks to make sure we can improve the quality.
You mentioned that you provide data to the community, and what was the response?
So it is in GitHub. I have so the paper is just published, so I haven't seen that much of citation yet. So 2 weeks ago I presented the paper.
No, but I'm using in terms of using the data that you generate. You didn't put that on GitHub or publishing the paper?
So no, it is just published. So let's see. Yeah, I would like to. Any other questions?
Questions? No? Thanks again, Hajar.
Thank you.